Okay, we're back, and we're still talking about limits, and what you remember from limits from calculus may well be limited, pardon the pun on that one, because you don't use them that often, but the thing that probably has stuck is the computation of limits, well, that is done through various theorems that tell us how limits behave, and those theorems, of course, also hold true for complex limits of complex functions. It's just that this time around, we're not just going to apply the theorems, but we're actually also going to prove them. And for that, we're going to use those epsilons and deltas that we hopefully have made some sort of friendship with up to this point in time, because we're going to go a little bit deeper with it now. So let's take a look at the next result here. Take a deleted neighborhood of z0. Take two complex functions, lowercase f and capital F, that are defined on that deleted neighborhood of z0, and assume that the limit as z goes to z0 of lowercase f is lowercase w0, and that the limit as z goes to 0 of capital F is capital W0. Then the following hold. The limit of the sum lowercase f plus uppercase f as z goes to z0 is lowercase w0 plus uppercase w0. The limit as z goes to z0 of lowercase f minus uppercase f is lowercase w0 minus uppercase w0. The limit as z goes to z0 of lowercase f times uppercase f is lowercase w0 times uppercase w0. And if the limit of uppercase f as z goes to z0 is not 0, then we can also talk about the quotient. And the limit as z goes to z0 of lowercase f divided by uppercase f as z goes to z0 is lowercase w0 over uppercase w0. So this is a theorem that is very natural and very easy to remember, because basically what it says is that the limit just moves through the algebraic operations, right? The limit of a sum is the sum of the limits. Limit of a difference is the difference of the limits. Limit of a product is the product of the limits. Limit of a quotient is the quotient of the limits, provided that we can form that quotient, which is why we have that capital W0 should not be equal to 0. Proving these things is now a little bit harder, and those proofs can take quite a while. Now the limits for sums and differences, those proofs are actually close to, in the level of difficulty, close to the proof that limits are unique, which is why I don't want to present those, and I think they might even be assigned as homework problems. But then the limit for the proof for products is actually nothing to sneeze at. That one actually takes some doing. So let's take a look at that one. And let's go through it with the same philosophy as what we had before. Let's first think about, let's first verify that all the steps are true, that all the steps are allowed, and then at the end go back and check where the ideas may have come from. So we let epsilon be greater than 0. And well, then there is a delta lowercase f, so that for all z with z minus z0 smaller delta lowercase f, we have that lowercase f of z minus lowercase w0 is smaller than epsilon over 2 times uppercase w0 absolute value plus 1. Well, that is quite horrible. Again, let's not think about why we may need that. We'll see why we need all that in the final estimate. But let's make sure that works out. Well, it works out because for every epsilon there is a delta, so that we can get that inequality. So I can just find that for an epsilon prime, which is epsilon over 2 times w0 absolute value plus 1. And I put w0 absolute value plus 1 in here because w0 could be equal to 0, and I don't want to divide by 0, of course. Okay, and we also have that for z minus z0 small delta f, we have that f of z minus w0 is smaller than w0 absolute value plus 1. That's another simple estimate with the triangular inequality, because, well, what we ultimately, it's not even the triangular inequality. We just use another epsilon double prime, which is W0 absolute value plus 1, and we can make sure that this thing is smaller than this epsilon here also. Now, why we want to do that, we'll see later on. Basically, the idea to read an analysis proof linearly is to be completely unscrupulous, and if there are some fancy things here and here, just ignore them, just make sure that it can be done. And again here, W0 absolute value plus 1 is used because if W0 absolute value was 0, well, we couldn't find then a delta, so that works. But even if W0 absolute value is 0, we add 1 and we can find a delta so that this difference here is smaller than 1. Okay, moreover, there's a delta capital F greater than 0, so that for z minus z0 smaller delta capital F, we have that capital F of z minus capital W0 is smaller than epsilon over 2 lowercase w0 plus 1. So again, there is a delta F, so that for z minus z0 smaller than delta F, we can make f of z minus w0 small. Okay. Let delta be the minimum of delta lowercase f and delta capital F. Remember, that was a step we also had in the proof that limits are unique. We have two deltas, and because we want both or all the inequalities that are true when z minus z0 is smaller than either of the deltas is satisfied, we want to have all of those inequalities to be true, so we choose our final delta to be the minimum of all the other ones. Then for z minus z0 smaller than capital delta, well, notice that then we have that this is true as well as that is true, which means we will be able to use this inequality, sorry for the quality of the highlighting, as well as this inequality here. And we will. So now we're interested in lowercase f times capital F of z minus lowercase w0 times capital W0, which is what we ultimately must make smaller than epsilon. Well, remember, there are two tricks, adding 0 and multiplying by 1. We add 0, and basically, well, we'd like to factor something out, and we can't do that because the f's don't connect directly with the w's. But if I now put a mixed term in here, lowercase f of z times capital W0, and if those absolute values weren't there, this would really be just minus plus, so we're just adding 0. Then I have stuff that I can factor out, and then I just apply the triangular inequality and separate it in such a way that I've got lowercase f times capital F of z minus lowercase f of z capital W0, that's one absolute value, and lowercase f of z capital F of z minus lowercase w0 capital W0 as absolute value. And the inequality works out because obviously I've used our best friend, our new best friend, the triangular inequality. Okay, now I can factor stuff out. I can factor the lowercase f of z out here, and I keep a capital F of z minus capital W0. But that's something I can control. That's good. And here I can factor out a capital W0, and I keep a lowercase f of z minus lowercase w0. But again, that is a term that I can control. Now I use that the difference between z and z0 absolute value was smaller than smaller than delta. And so I know, for example, that f of z I need to have that f of z is smaller than w0, not f of z minus w0 smaller than w0 plus 1. Okay, I could start over again, or I could fix it, but I think here's also a good opportunity to show how you fix something if you didn't quite get it right the first time. So let me pause briefly. All right, well, I'm back, and I fixed it. Now we have to figure out what I fixed and well, whether it works or not. So let's see. The only thing I've changed is that I claim at the beginning that there is a delta f greater than 0, so that for z minus z0 smaller delta f, we have the inequality that we claimed before, and f of z absolute value being smaller than w0 absolute value plus 1. That's the only change I've made. Why is that still true? Because, of course, you cannot write down a proof where you first write down the first half and then You just change something randomly and hope that it works. So this still must work. Well, okay, the limit of lowercase f is w0, so it stands to reason that when z is close to z0, then f of z can't be too far away from w0, and that means its absolute value should be smaller than w0 absolute value plus 1. Okay, so it makes sense. That's not a proof yet, and in fact the proof would be something that I would actually recommend you write down with paper and pencil as I talk you through it. It's a good exercise in mentally going through this stuff and using the triangular inequality again. Because if I want to control f of z, well, I can always add and subtract w0, right? So f of z would be, absolute value would be smaller than absolute value of f of z minus w0 plus the absolute value of w0. The absolute value of w0 then doesn't change anymore. And f of z minus w0, I can make that arbitrarily small, which means in particular, I can make it smaller than 1. So that means as long as I choose my delta the right way, this really does work out. Okay, let's keep going. As we've just established, for z minus z0 smaller than delta, yes, we can get that f of z absolute value is smaller than w0 absolute value plus 1. Boy, that highlighting is terrible. Capital F of z minus capital W0, well, that's smaller than epsilon over 2 W0 plus 1, W0 absolute value plus 1. So we get that. Lowercase f of z minus lowercase W0 is smaller than this thing here, which is epsilon over 2 capital W0 absolute value plus 1. And the W0 absolute value here just stays with us. Okay, and now we can see, well, the first few times that you read that, it almost feels like a miracle, but it's actually just that it's been set up that way. It all cancels out, right? W0 plus 1 over W0 plus 1, that's gone, so that's just epsilon halves. And W0 over W0 plus 1 is smaller than 1, so this thing is smaller than epsilon over 2. And that means that the whole thing is smaller than epsilon. And that is the proof, right? Because we have shown that for every epsilon greater than 0, there is a delta which is greater than 0, so that for z minus z0 smaller than delta, we have that the difference between the product of the functions and the product of the limits is smaller than epsilon. Okay, so that proof works out. Now let's think about it again, and this is the kind of thing where mathematical reading changes a little bit from calculus. Calculus, if you've got the right amount of brain power, and I think you do, you can basically read linearly and everything works out. Mathematical proofs, you read over and over again, and you read them in different ways and sometimes also in different directions. Remember, an analysis proof typically is driven by the final estimate, right? So how does that final estimate come about? Well, you basically start out with just this difference on a blank sheet of paper, and you try to figure out, well, how on earth can I make that smaller than epsilon? Okay, and you realize these don't communicate with each other, but whenever you've got two products that don't communicate with each other, if you just insert a mixed term, lowercase f times capital W0, capital F times lowercase w0, or any other kind of combination, but I think typically I'd like to also mix lowercase and capital stuff. Anytime you do that, you realize that you get a connection where you can factor something out. So that's where you get the idea that the lowercase f times the capital W0 probably should be spliced in between here. And as soon as you've got that, you realize you can figure out the f, which is nice, and the rest that remains are terms that we can control, namely lowercase f minus lowercase W0 and capital F minus capital W0. That's, I think, also why you want to mix lowercase and capital stuff here, because otherwise you don't get the right differences factored out. As soon as you can control that, you have to start thinking, well, how can I make all of this smaller than epsilon? Well, I've got two terms, so obviously I'll have to deal with epsilon halves in these two literally separate trains of thought. And the easier one then is the latter term, because here we just have a number, and the way you get rid of a number is to divide by that number, and to make sure that that nothing goes wrong when the number is 0, you divide by the number plus 1. So that gives us the epsilon over 2 W2 to capital W0 absolute value plus 1, which is what we had over here. And you certainly want to do the same thing over here, but the f of z is not constant. That's why you first have to think yourself through the fact that you can make the f of z smaller than some kind of constant. Remember, f of z is close to W0, which means that f of z absolute value should be smaller than W0 plus 1, and you can work that out with a triangular inequality. F of z minus W0 absolute value can be made smaller than 1, which means if I go with plus minus W0 here, I get f of z minus W0, which is smaller than 1, plus W0 absolute value, which I keep. So I get this upper bound here. Highlighting is terrible. And then that means I now need to somehow control this thing with something that cancels the W0 plus 1, and that's this term over here. And then, of course, everything works out to be epsilon. Now notice that if I had worked this proof out on a board in class, I really sometimes do that in analysis class, that I first write down the final estimate and then I write down the header, because the estimate tells you what you need, and then you actually also get the header right. If I had done that, and if I could do this kind of thing with these kinds of panels, I wouldn't have made that mistake up here. All right, that being said, I think we've gone through one of the harder proofs for a while. Let's see what else is in store for us. If you have a polynomial, and of course polynomials are very natural functions to consider, and you've got a point in the complex plane, then the limit as z goes to z0 of the polynomial is the polynomial at z0. And the proof of that now is actually very much calculus style. Now that we've got these powerful laws, we realize the limit of the polynomial is the limit of, well, the expression that gives us the polynomial, but the expression is a sum. And the limit of a sum is the sum of the limits. So I can take this as the limit of a0, limit of a1z, a2z squared, and so on and so on. But the limit of a constant is the constant itself. So we get a0 here. The limit of a product is the product of the limits. So the limit of a1 is a1. The limit of z is z0. The limit of a2 is a2. The limit of z squared, remember, that's just z times z. So that's 0 times z0, which is z0 squared. And you go all the way through to the end, and you get that this is really just the value of the polynomial at z0. And that's already the end of the proof. Okay, so those limits can keep us rather busy. I think this is in fact another separate section in the text, so if you want to, go ahead and pause the presentation right here, go through some of the homework problems for that section. Some of those things probably will be proofs, and they can take quite a while, but remember, you can get through that. It will probably take longer than a standard calculus problem, but it's not impossible. Limits at infinity now, or limits involving infinity, is basically just a little bit of shifting gears. And the way Churchill and Brown do it is they reduce all the limits that involve infinity to limits that actually involve only finite numbers, which I find in retrospect actually rather elegant. It's the first time that I've seen it approached that way, as far as I recall. My memory may be faulty there, but I've done mathematics for a long time, and if I have seen this approach at all before, then it was a long time ago. So it's not really very standard, even though it has something to it. Let's observe that the function t of z equals 1 over z, which maps every number to its reciprocal, that thing has the following properties. It's undefined at 0, and circles of radius r are mapped to, circles around the origin of radius r are mapped to circles around the origin of radius 1 over r, which means small numbers are mapped to large numbers and vice versa, right? If r is small, 1 over r is large. If r is large, 1 over r is small. So that means this function in some ways just swaps 0 and infinity. And that's the key to the definition of all the limits that to all the definitions of limits that involve infinity. So take omega be a subset of z, of c, of the complex numbers, and suppose that that thing contains the exterior of a disk around 0. So let's not think of the disk, but let's think of everything that's outside that disk. And let the complex function f be defined on that exterior of a disk. So this is a function that can reach, so that for which the inputs can reach infinity, if you will. Then w0 is the limit of the function f at infinity, if and only if for all epsilon greater than 0, there is a delta greater than 0, so that for all z and omega, so that z absolute value is greater than 1 over delta, we have that f of z minus w0 is smaller than epsilon. So it's the same hierarchy as before, and that is something where the repetition will also help us remember the definition. Anything that involves limits typically is for all epsilon greater than 0, there is a delta greater than 0, so that the following happens. And here, what do we want? We want for large z, so for z being greater than 1 over delta, epsilon and delta are both considered to be small, so going with z absolute value greater than 1 over delta just means that we're getting rather large there. We have that f of z minus w0 is smaller than epsilon. So that means the intuitive idea that when your numbers get close to infinity, your input numbers get close to infinity, then your output numbers ought to get close to the limit. That's exactly what this encodes. The notation is that the limit as z goes to the infinity of f of z is w0. And we're going to go through 4 of those things actually. So let's now talk about a deleted neighborhood of z0. Let the function be defined on omega. And let's talk about infinity being the limit of the function at z0. Well, that's the case if and only if. Well, we can also already predict the beginning. For all epsilon greater than 0, there is a delta greater than 0. So that for all z and omega with z minus z0 smaller than delta, we have that f of z absolute value is greater than 1 over epsilon. Remember that technically we could actually just say greater than epsilon, but remember the connotation is epsilon is small, which means the connotation then would be that 1 over epsilon is large, and so that means this definition just says when z is sufficiently close to z0, then f of z gets incredibly large. And that's what an infinite limit should be, right? As you get close to the point, your function blows up. The notation is that the limit as z goes to z0 of f of z is equal to infinity. Third one, well, let's see. We're going to talk about a domain that contains the exterior of a disk around 0, and we want to have the complex function again be defined there. And we want to talk about infinity being the limit of the function at infinity. Well, how should that work out? That would mean that for large input values, the output for large input values, and that's encoded by the at infinity, the output values should also be large. So that should be if and only if for every epsilon greater than 0, there is a delta greater than 0, so that when z absolute value is greater than 1 over delta, large input value, we have that f of z absolute value is greater than 1 over epsilon, large output value. Let's see if that really is the case. If and only if for all epsilon greater than 0, there is a delta greater than 0, so that for all z in the domain, so that z absolute value is greater than 1 over delta, we have that f of z absolute value is greater than 1 over epsilon. I think the reason why the way Churchill and Brown set this up isn't that common in other texts is because, well, you've got the 1 over deltas and the 1 over epsilons here, which people often don't like that much. But, I mean, in some ways, the nice thing here is we keep the repetition going. We keep grinding almost literally into our mind that limits are always for all epsilon greater than 0, there is a delta greater than 0. And there's something to be said for that. That repetition breeds familiarity, and that will help us work with this stuff a bit more easily. Okay, so the notation is that the limit as z goes to infinity of f of z is infinity. And now we actually talk about some theorems. We take z0 and w0 both to be complex numbers. Then the following hold. The limit as z goes to z0 of f of z is infinity if and only if the limit as z goes to z0 of 1 over f of z is 0. Well, that makes sense, right? If f gets large, then 1 over f gets small. If 1 over f gets small, then f gets large. The limit as z goes to infinity of f of z is w0 if and only if the limit as z goes to z0 of 1 over z is w0. Well, that's because if the input values z get large, that's the same as saying that we can send this z to 0 and then 1 over z gets large. Similarly, if this z goes to 0, then 1 over z gets large. The limit as z goes to infinity of f of z is equal to infinity if and only if the limit as z goes to 0 of 1 over f of 1 over z is equal to 0. Output gets large means 1 over the output gets small. Input gets large means 1 over another input that goes to 0 would get large also. Okay, the proof, I think we're not going to do the whole proof, but for every statement, the key to the proof really is that, informally speaking, the function z maps to 1 over z, that function interchanges 0 and infinity. For example, for part 3, what do we need to do? Consider the situation that the limit of f as z goes to infinity is infinity. Well, then for every epsilon greater than 0, there is a delta greater than 0, so that for all z absolute value greater than 1 over delta, we have that f of z is greater than 1 over epsilon. Well, that means that for all z absolute value smaller delta, we have that 1 over z absolute value is greater than 1 over delta, which means that f of 1 over z is greater than 1 over epsilon, and hence 1 over f of 1 over z is smaller than epsilon, and if I subtract a 0, that doesn't change anything. And that says that the limit of 1 of f of 1 over f of 1 over z as z goes to 0 is in fact 0, which is what is stated here, so I wouldn't have needed to break my tongue on that one. And the converse, which says that the limit as z goes to 0 f of 1 over z equals 0, implies that the limit z going to infinity f of z equals infinity, is actually proved very similarly. So you can see here how Churchill and Brown have set that up very skillfully, because you work with reciprocals in the right places. The translations to limits that involve finite numbers in the input as well as finite numbers in the output is very, very fluent here. I leave that other direction to you. It may even be an assigned homework problem, but it certainly is well worth thinking about to just get more familiar with these ideas. Okay, example. The limit as z goes to 2 of z plus 1 over z minus 1. Well, that should blow up, right? Because you divide by 0, and we know from calculus when you divide by 0, stuff blows up and it's infinity. So that is infinity, yes, but why is it infinity? It is because the limit as z goes to 2 of the reciprocal, z minus 2 over z plus 1, sorry, is equal to 0, because as z goes to 2, the numerator goes to 0, the denominator goes to 3, and 0 divided by 3 is 0. So we have a watertight justification here using theorems that we already know. Similarly, the limit as z goes to infinity, z plus 1 over z minus 1, well, we know from calculus how to work that, right? That's, you expand with 1 over z in the numerator and in the denominator, and then you get 1 over 1, and that's 1. So that limit, and therefore would be 1. The approach that we would do here with the preceding theorem is the limit as z goes to infinity is the same as the limit as z goes to 0 with all the z's replaced with their reciprocals, replaced with 1 over z, which is what we've done here. So that comes from the preceding theorem. Okay, but now this one we can work out because we can find the common denominator. So this is the limit as z goes to 0, 1 plus z over z divided by 1 minus z over z. And it turns out that as we simplify that, that actually is the same one. I don't think that happens all the time. That is probably specific to just this problem. But it's the limit as z goes to z0 of 1 plus z over 1 minus z. And that ends up being 1, as we also claimed before. Okay, the limit as z goes to infinity of z squared plus 1 over z squared minus 1. Well, that's quite terrible, because now, well, no, that's not that bad, because we're still going to infinity, so we do the same approach, right? That's the limit as z goes to 0 of 1 over z squared plus 1 divided by 1 over z minus 1. Common denominators, 1 plus z squared over z squared, 1 minus z squared, 1 minus z over z. Simplify that, we get the limit as z goes to 0, 1 plus z squared over 1 minus z times z. So you can see that certainly is no longer just the same as that one. But now as z goes to 0, this one goes to 1, this one goes to 1, but the z at the end goes to 0. So that limit is infinity. The limit is infinity because the limit of the reciprocal as z goes to 0, 1 minus z times z over 1 plus z squared. That is 0 because this guy goes to 1, this guy goes to 0, and this guy goes to 1. So we get 1 times 0 over 1, which is 0. All right. Now let's talk about continuity. If you wish, go ahead and take a break because we've finished another section, if you will. It's just that this whole presentation addresses the same overarching topic, and usually this is done in 1 or 2 class periods where all the related things are talked through. So continuity. A function f is called continuous at z0 if and only if f of z0 exists, and the limit as z goes to z0 of f of z exists, and the limit as z goes to z0 of f of z equals f of z0. Again, if you wish to go back to your calculus text, this is pretty much verbatim the definition from calculus, because now we have formally defined limits and everything. This is a watertight, formal mathematical definition, and the reason why this definition now connects to complex variables is, of course, because we're assuming here that this function maps complex numbers to complex numbers, but this is otherwise something that is at least somewhat familiar. Okay, now f is called continuous or continuous on its domain if and only if f is continuous at every point in its domain. The theorem is that f is continuous at z0 if and only if for every epsilon greater than 0 there is a delta greater than 0, so that for all z in the domain with z minus z0 smaller delta, we have that f of z minus f of z0 is smaller than epsilon. So continuity can also be encoded in terms of epsilons and delta, and that's good because sometimes we really have to get technical with continuity. But notice, and I went a little bit fast here, notice that of course the big thing about continuity is continuous functions are the ones for which limits work out nicely, where you get limits by just plugging in the number. Okay, and the epsilon delta stuff, notice that I didn't even put a proof in here. This is something, it's verbatim just encoding the epsilon delta definition of this part right here, going back and forth. Okay, theorem, if you've got two functions, so that z0 is in the open domain of g, and we assume that the domain is open, and g of z0 is in the domain of f, and so we implicitly assume that the domains are both open. Then we say the following: if g is continuous at z0 and f is continuous at g of z0, then f composed with g is continuous at z0. Now, from our limit laws, it's actually fairly easy to derive that continuity is preserved by addition, multiplication, subtraction, and division. But there's one more thing that we can do with functions that we can't do with numbers, and that is we can plug one function into another function. And so we would certainly like to have a result that says continuity is also preserved by the composition of functions. And it is. All these technical hypotheses basically just says the composition of two continuous functions is continuous. And the proof, and I think we'll go through the whole thing here, it's just a staggered epsilon delta argument. So let epsilon be greater than 0. Because f is continuous at g of z0, there is a delta f greater than 0, so that for all y, and we really want a y here because essentially that's in an intermediate stage, right? F composed with g is f of g, so f doesn't input the z0s, f inputs the g of z0s, and we call those things y here. For all y, so that y minus g of z0 is smaller than delta f, we have that f of y minus f of g of z0 is smaller than epsilon. That is just the definition of continuity of f at g of z0. It's just a little bit of a pain to put in all the notation. Because g now is continuous at z0, for delta f, not for epsilon, for delta f, for the one in the middle, there is now a delta, and that'll really be the delta that we will use for continuity of f composed with g, so that for all z with z minus z0 smaller than delta, we have g of z minus g of z0 smaller than delta f. That's again straight from the definition of continuity for g. It's just that we use delta f instead of epsilon here, which is something we can do. We can always rename our variables even though epsilon and delta are typically used in certain places, they are dummy variables, just like integration variables, where if you integrate x squared dx or if you integrate t squared dt, you get the same result just with a different variable. Okay, so that being correct, we can say now that then because for z with z minus z0 smaller delta, we have g of z minus g of z0 smaller delta f, we have, well, that this g minus g of z0, the g of z now is one of those y's, and so we can infer that therefore f of this y, so f of g of z minus f of g of z0 is smaller than epsilon by what we had derived in the second sentence of the proof. Well, therefore we have proved that for every epsilon greater than 0, from here, there is a delta greater than 0, which we encountered here, so that for all z with z minus z0 smaller than delta, which we got here, we have that f of g of z minus f of g of z0 smaller than epsilon, which we got here. So we have verified the definition of continuity for f composed with g at z0, and so that means f composed with g is continuous at z0, and that is the end of that proof. Again, a lot of stuff between the lines, a lot of words to follow, a lot of things where you really have to think very carefully, which is one of the reasons why advanced mathematics reads even more slowly than calculus, but it is well worth it, because as you are learning to read that precisely and as you are learning to verify every single step, you're becoming a much more critical reader than you were before, and that actually helps in all sorts of walks of life. I mean, it helps me as an administrator when I have to read through some rules that have to be applied in a certain way. Well, I'm now through mathematics accustomed to checking all cases, and so I know if there is a loophole or if there isn't, and then depending on whether I'm trying to close a loophole or opening a loophole, I will be either happy or sad, and no, I'm not going to not tell people about a loophole that exists, or or try to pretend that there is a loophole when there indeed is not. Alright, yeah, honesty is best policy in these kinds of things. Okay, let's finish out the continuity. We're close to the end here. Hooray, right? You can see this indicator, I think, also in what's being recorded on the screen. If f is continuous at z0 and f of z0 is not equal to 0, then there is a neighborhood of z0 on which f has no zeros, which is rather nice, because basically that means that zeros can't just cluster up around a point where the function in fact is not 0 itself. The proof, well, we let epsilon be greater than 0, but we want epsilon to be f of z0 absolute value, so it's another one of those where we find out at the end why the choice of epsilon was the way it does. But remember, if something works for all epsilon, well, then I can certainly choose my epsilon to be f of z0 absolute value, which is not equal to 0 and therefore greater than 0. Well, for that thing there is a delta, so that for z minus z0 smaller delta we have f of z minus f of z0 is smaller than epsilon. Yeah, sure, definition of continuity works. So therefore, for z minus z0 smaller than delta, we have f of z absolute value is f of z minus f of z0, no, is f of z0 minus f of z0 minus f of z in parentheses. Well, is that really true? Yes, it is. F of z0 minus f of z0 is 0, and minus minus is plus, which even wouldn't have mattered because we have an absolute value here. So those two are equal. Our new best friend, the reverse triangular inequality, says that this is greater than or equal to f of z0 absolute value minus the absolute value of the rest, which is f of z0 minus f of z. Basically, the triangular inequality always works when you want to make an absolute value smaller than two other absolute values. If you want to make an absolute value greater than two other absolute values, or greater than the difference of two other absolute values, you use the reverse triangular inequality. Here's one of those stages where you may want to go back in the book or to the requisite presentation, to the slides, to just make sure that that you remember the reverse triangular inequality. But again, that verifies that that works. And that means this is now greater than, because, let's see, f of z minus f of z0 is smaller than epsilon, which means that this difference, these minuses make sure that this is greater than f of z0 minus epsilon, and that epsilon was f of z0 absolute value. And so that means that's equal to 0. And so that means for all z minus z0 smaller than delta, we have that f of z is greater than 0. And that's what we want to prove. We have that f of z is not equal to 0 for all z minus z0 smaller than delta. And that's the end of the proof. The bar has reached its end too. This is the end of the computation, which would be, or which is the end of the presentation, which would be rather nice. But how on earth do you think of this stuff? And believe me, I'm not trying to toot my own horn here. It's not like I invented all this stuff. Most certainly I did not. And most certainly I asked myself exactly the same question as I was at a similar stage in my career. How do you get that idea? How do you choose your epsilon to be f of z0 and all that other stuff? And again, remember, the rule of thumb really for me now and for any student whom I talk to in this subject is the key is always in the final estimate. And so what do I want to prove? I want to prove that f of z0 is not equal to 0, and I'm dealing with complex numbers. I'd much rather deal with real numbers. And so working with absolute values to work with f of z absolute value actually is quite natural. And then, of course, I can work with inequalities, right? On the complex numbers, I can't work with inequalities because the complex numbers cannot be ordered in a way that actually interfaces nicely with the algebraic operations. That's an abstract result that I'm only mentioning. It would take a while to explain, but basically, if we could order the complex numbers, we would have done it. Okay, so I can work with absolute values here, and that way I can work with inequalities. All right, what can I control? I can control the difference between f of z and f of z0, and I can make that small. So it makes sense to shift in this f of z minus f of z0, and then again, with enough experience in the triangular inequality, we realize that the absolute value of a difference is always greater than the difference of the absolute values. And here's where, well, because I want to make this greater than 0, I want to have a fixed number that I know that is not 0, so it makes sense to split it off in such a way that I get the f of z0 here. And then I have something here which I can control, which I can make small. How small must I make it? I must make it smaller than f of z0, absolute value, to make sure that this is greater than 0. Aha! That is where this epsilon at the beginning comes from. Ha! You've lost my handsome face. Well, you may have been happy about that. I'm not sure how great I am to look at, but nonetheless, it's also intended for me to actually have an opportunity to look at you here, to get some contact on this, for you to also see, hey, look, I'm not trying to pull one over to you, on you. I'm actually quite enthusiastic about this stuff, still quite in awe of all these things that very, very smart people have figured out to put analysis on a rigorous footing. And we have seen here now, on one hand, as we went through it, that the proof is true, and as we went back through it, I hope you also got a good idea as to how people can think of these proofs, because, well, you may have to produce some of those proofs on the homework. Now, let me tell you again, face to face, as I learned these kinds of proofs, that was hard for me too. That is also why I'm harping on this stuff so much, and why I'm trying to figure out ways to explain it like I have done here, because I'm not ashamed to admit and acknowledge that, yes, this stuff is hard. I hope that the explanations have helped. I hope that you take like a fish to water with these kinds of things, and that these proofs work rather well for you. Even if, hopefully when they work rather well for you, you may feel a little bit insecure about those things, but that is, of course, where I come in. That's where you email me. That's where we try to have a phone conversation, or where you just send me something just asking, look, is this right, or am I completely off base? That's certainly something that I'm here for. Of course, on the other hand, the more stuff you get right away and just submit to me, the easier my job is. But the point of this class is not to make my job easy. The point of this class is for you to learn a rather challenging bit of mathematics. Now, what I can also promise you is we're going to hover at this level, I think, for half of the next presentation, because we're also going to prove differentiation rules. But as we're running out of disk space also again, we are very soon going to go back to a more calculus style approach where we are using the rules that we're proving. So with that in mind, get to the homework, handle another hard part of the course. I'll see you in the next presentation.